learning is basically learning involving labeled data. So someone's already labeled the data for you, or the data comes with labels. That's why it's called supervised. You imagine a supervisor that's applying labels to the data. And your task, well, we'll get into this more, but your task is to put the correct label on the data usually. Unsupervised learning is more about unlabeled data. So you just have data, and then you have to figure out a useful way to break it down or understand it. So it might be to figure out which features of the data are most useful, or it might be to divide the data into groups or something like that. And finally, one I won't talk much about, but it's reinforcement learning. It's even further removed than that. It's like you don't even have data at the beginning. What you have is like an environment where you can explore and collect data, then figure out what to do with the data. So it's like a maze where you're walking around and collecting treasures or punishments, or like little meeting enemies in the maze or something like that. And then you're trying to figure out what's the best way to walk through the maze to sort of find rewards and avoid enemies, or something like this. But there's all kinds of different variants of reinforcement learning. So I would say that basically what these are capturing is settings where you have more or less a priori knowledge about what you're supposed to be doing and about what data would be useful to look at. So that's one way of breaking down these different learning tasks. So to get into a bit more detail on one of them, supervised learning is usually like this. Usually you have labeled training data, and here I'm using an example of images that could be labeled as A or B. And here it could be alligators or bears. And what you're looking for is some function that you can input an image into, and you might input the image as a vector of numbers, usually, where you just say every pixel is mapped to a number, and then I input it into this function. And then the function outputs a single number. In this case, that's all we need. And if the number is positive, the function is saying it's an alligator. And if it's negative, it's saying a bear. And that might not be right, but we try to change the function around until that is as right as possible for the data that we have. And how do you do that? This is the important idea of a cost function. So what you do is you say, we have to have some notion to tell the computer how good the function is. And there's all kinds of different ways to construct these, and there's a whole bunch of philosophy about which one is best and what kind of probabilistic Bayesian priors they involve, and it's a whole thing. But a very simple one is basically just to say, let's come up with an ideal function that, in this case, I made it an indicator function that's just +1 on all the alligator images that we know, and -1 on all the bear images that we know. And so this yj is like a function over our data set. J runs over the data set. It's sort of just some enumeration of the data set. You know, j equals 1, that's the first image. Of j equals 2, that's the second image, and so on, in some arbitrary order. And f of xj is plugging in the jth image vector into our function that we're trying to improve. And then all this is doing is saying, how different is the output of our current function from this idealized function that would do a perfect job on our data. And then what we do is we have some way that we vary the adjustable parameters of f, which I haven't shown here, but imagine f has all these adjustable parameters. It could be just 2, it could be millions. And then we vary this in some way with gradients or maybe randomly, and there's all these different strategies. And we keep looking at this cost function and we try to make it go down. So it basically just in this high dimensional function space of all the possible outputs and all the inputs, it measures the distance of the trial function from this ideal function. This is a very common setup in machine learning, and you can tweak it all different ways. Unsupervised learning, I'll be brief, but there's different versions of it. So a very common one is that you have data that's unlabeled, and then you just want to find a function so that the output of the function is close to the true probability of observing that data. So you don't have all the data, but you have a lot of it. And you see certain things happen with some certain frequency, and you want to try to learn the probability of seeing other data you don't have. So you're trying to learn a hidden probability distribution. And usually that your function just is trying to be the probability distribution. But there's another version of it that you could call a Born machine, which is when you want the square of the function to be the probability distribution. Why not? You know. And another very different one is you're trying to find clustering of the data. You're trying to say, I have all this data, let me try to find dividing lines in this high dimensional space that divides this kind of thing from that kind of thing. So it could be the alligator bear example. It could be that you don't label it as alligators and bears, but the machine just figures out that's the right way to divide these images. And one other one I mentioned before is discovering some kind of reduced or compressed representation of the data that's useful as a preliminary step for other learning tasks. So you might want to say, these images are too complicated, there's all this color, there's all these details. Maybe all we need to do is count teeth of these animals, and that's all we need to feed into the next pipeline of learning to decide whether they're alligators or bears. So that's another way of doing unsupervised learning. So overall, the general philosophy of machine learning is that there's this vast, impossibly huge space of functions that would solve our problem perfectly. So that's like these indicator functions, but they don't have any structure, at least not that we can easily put into a computer. So there's some function out of the whole space of functions y that will definitely solve our problem. It's almost just defined to solve our problem. So what we'll do to try to get near that ideal solution is we will parameterize some very flexible set of functions. So think of like a neural net, but which is mostly chosen not for being so correct or that we know that it's this perfect function. It's more that it's very flexible. It can fit lots of things and is very convenient to optimize in some way. It's sort of, you know, cheap to work with on a computer. Then we say of all those functions from this class that come closest to our ideal solution, we want the simplest one. So the one that perhaps has the fewest parameters or some other measure of simplicity. Maybe it's the smoothest. And then by imposing that last condition, we hope that it will generalize, that it will continue to be close to this ideal solution for data we haven't encountered yet. That's the philosophy basically. Okay, so that was just a very quick.
Yep.
Okay, good. Okay, perfect. Great. Okay, well, that was actually kind of timely spot if we're going to get kicked out anywhere between these sections. So now let me briefly say that that was machine learning at a very, you know, kind of lightning introduction to it. And so now let's talk about tensors and machine learning. Do these have a place? Where do they come up? So I wanted to start at kind of a broader level than tensor networks, and just to say that already people discuss tensors in machine learning. If you go out into the machine learning literature, there's quite a lot about it, but it may be a little unfamiliar to physicists or may not be clear what's going on right away. So one very common use of tensors in machine learning is to be a way of representing the data. So this is one use of it, is that there's quite a lot of literature where instead of representing data as a vector of pixels, there's work being done where they say, okay, let's take each image, like say this image of a mushroom, and we'll have what they would call a three-way tensor, order 3 or rank 3 tensor, where one of the indices indexes over the x coordinate, one over the y, and then the last one goes over 3 values, which just says whether it's the red, green, or blue channel. And then all the numbers inside this tensor are just telling you about the RGB value of a given pixel. And then people try to use this tensorized structure of this image data to see if they can get these machine learning models to work better. Another similar example would be more like tabular data, which could be, say, medical data, where you have the data is not really sensible to be put into a matrix because you really have, say, 4 different axes, not just like 2. So why would you put it into a matrix, say? Instead, you might put it into a tensor with 4 indices. And then you fill up the entries of this tensor with all the cases, you know, where you have a person of a certain age, height, weight, and symptom category. And then the kind of things people might do on such a tensor is then compress it. And when you compress it, the missing entries actually appear again. This is something that's rather different from the experience of physicists using tensors. We think of there as some kind of right tensor that we're trying to find. Here, actually, and then compressing it introduces an error. But here you actually compress it, and it actually gets better. So missing entries actually come back that weren't there that you put in. So it's a very interesting thing. And this actually happens in tensor networks, but physicists had not been aware of it as far as I know. So that's something that people do. And I'm not going to say a lot more about that, but we can talk about it later. Another use of tensors in machine learning that's going on a lot right now is to use them as some kind of general compression tool. And then because people are very, you know, neural networks are very popular, that's the thing that people want to compress. So there was some influential papers a few years ago showing that if you actually replace a weight layer of a neural network, and this is I'm not going to go much into the definition of a neural network, but basically these rows of blue dots, what they are is you apply a element-wise nonlinear function on input vector, and what these messy cobweb-like layers are, all they are is a matrix. So this is just a very big matrix, and every line is just the element of a matrix. And then the next row is another element-wise function, and then another matrix. But in some of the more state-of-the-art neural networks, this matrix, what's called a weight layer, but it's really just a matrix, can be very big. And so what you can do is you can tensorize the matrix, which means you just say if it's a 2 to the n by 2 to the n matrix, you map it to a tensor with 2 n indices, very simple mapping. And then you replace that tensor by like a matrix product operator tensor network or some other kind of tensor network. And then you do gradient descent through the tensor network. And this is a way of compressing neural networks. So that's another use that people are pursuing. And finally, there's one that will be the one that I'll be pushing on in this talk and proposing, but it's already formally was something people knew for a long time, which is that when you write down certain high-dimensional models in this older style of machine learning that you could call kernel learning, which was really pretty much the state of the art all the way up until about 2012, that the adjustable parameters naturally have the structure of a large tensor. But that was usually something that was just kind of bypassed over as a formal step, and then usually people would replace this tensor with something else that you could actually store in memory and not work with it. But the idea of tensor network machine learning that I'll talk about is to say, no, let's just actually work with this huge tensor of parameters by putting a tensor network in its place. That'll be what we'll do. But I'll come at it in a little bit more pedagogical way. Okay, so why tensor networks as a tool for working with tensors? So if we encounter tensors in those different ways, as data, as a compression tool, or as maybe all the parameters of a model, as in this case, why would a tensor network be a good thing to use? And we'll see there's actually a lot of compelling reasons for this. So first of all, a tensor network is a very general and kind of simple idea. It's just to say, I'll define this notation very soon, by the way, if you don't know this notation, but you have a huge tensor that might have 10 or 100 or even an infinite number of indices. And you say, we can't really practically store that on a computer, not even close. Like once we have more than say 20 indices, it's pretty hopeless to store that whole thing. The number of components grows exponentially in the number of indices. But what we could do is we could store a bunch of smaller tensors that share some indices that are summed over, but where the number of indices that are left unsummed is the same number as in our original tensor. So formally, these things live in the same space. This one just occupies some little corner of that space. So we can hope that maybe the important cases of this tensor that we're interested in can be captured as a contracted product of a bunch of smaller tensors with some indices left unsummed. And you actually get a ton of benefits from this idea. If this idea works for your case, you get an exponential reduction in memory needed, an exponential speed up of many important computations, like adding these tensors or dot producting them together. But more than that, you get theoretical insights and interpretations of what's going on. You get powerful tools like filling in missing entries, given only partial entries. And then you get lots of optimization algorithms that are very interesting, and I'll discuss a few of those briefly. So let me now kind of formally introduce this notation, but very briefly, because I think probably a lot of you have seen it before, but stop me if you haven't. This notation is called Penrose tensor diagram notation. And the idea of it is that classical notation can be quite a lot. Sometimes you have to name all the indices, and sometimes that means putting subscripts on them, and sometimes those have subscripts. And also, it can just be very hard to look at expressions involving lots of symbols like this and really work out what's going on. So having these drawings is much easier in many cases. And what you do is every time you have a tensor, you draw it as some shape, and then the shape is not so important. And then the lines coming out of the shape are each of the indices. And this is just some examples for familiar low dimensional cases. So you can have a vector, which is a shape with one line coming out of it, or a matrix is a shape with two lines, and a tensor with 3 indices would have 3 lines. And you can put the names if you want, but one of the powers of the notation is that in many cases, you can leave the names off without really any loss of what's going on. And the key rule of this notation is that when you join 2 lines coming from 2 different tensors, then there's a sum happening on that line. There's a summation of that index. And this really comes from the idea, this kind of familiar bookkeeping tool in traditional notation, where if I say this example of a matrix mij times a vector vj, and I sum over j, sometimes you'll see you might put a line to help yourself find the 2 different copies of the index j. And the idea of this notation is just to promote this line to being the sum. So instead of having this giant symbol and naming j and all those things, you just have this line, and it tells you this is summed over with that, over all the values that it can take. And it has a lot of nice advantages. Like for example, on the left, you can see that whatever is going on here, there's 1 index left over. So the result is a vector. It's a little harder to see over here. You have to kind of hunt through and say, okay, I have 1 index left over, and so it's a vector. And then here I'm starting to drop letters. And so you see I have something with 2 indices, another thing with 2 indices, and it's summed over on 1 index. And I can also see that whatever is going on, the result has 2 indices. So I can immediately see that this thing results in a matrix. And that's the product of 2 matrices, and we know that results in a matrix. And then we can see that for this third example, whatever's going on results in a scalar, because there's no indices left unpaired. And so that's the trace of a product of 2 matrices. And you can even visually see that this has a cyclic permutation symmetry, because I can take this matrix like as a bead on this ring and I can pull it around the back. So you can actually prove some theorems even just visually in this notation. But it's every bit as rigorous as traditional notation. It's just a different notation. So now using this notation, we can discuss tensor networks a bit more detail. The best understood and most well used and sort of most researched for lots of good reasons tensor network is the matrix product state. And that is depicted here. So that's if you have a large tensor within indices and you break it into a chain of tensors, most of which have 3 indices, as you can see. Each of these has 3, 3, 3. And then they have 1 index left on some each. So they're like, each one carries one of the original indices and then 2 other what are called virtual indices or bond indices or link indices. There's different names for them. And then they're all just strung together in this chain-like pattern. And to help you read the math literature, if you go off looking at math literature on machine learning, this is known as a tensor train. And these indices, the size of them is called the tensor train rank of the tensor train. So this was something that was discovered in 2011 in math, and it's equivalent to matrix product state. So it's starting to get a lot of currency in the math field. Why is it called a matrix product state in physics? Well, that's referring to how it's a compressed way to store and retrieve tensor elements. So if you say, I'm asking for the 0, 1, 1, 0, 1 element of this tensor, the element where the indices are set to these values and they're held fixed. So we know that's a scalar, that's some number that we're looking for. So what we can do is we can clamp these index lines that are sticking out, we can clamp them fixed. And when we do, we don't have to draw them anymore. Now these leftover pieces are just like slices of these original tensors. They're just leftover pieces where these indices are held fixed. And you can see that most of them are matrices. This one has 2 indices, this one has 2 indices, 2 indices. So it's a chain of matrices all multiplied together. The first matrix is a 1 by something, and the last one is a something by 1, or you can think of it as a vector. And so all we have to do now is multiply this chain of matrices. And the way to do that is to do it 1 by 1, so or pair by pair. You do these 2, then you're going to do these 2, then these 2, and these 2. That's the efficient way to do it. And when you're done, you get a number, a tensor with no indices coming out. And that number is this MPS matrix product state approximation of that tensor element. You can think of it either as an approximation or as just a parameterization where it sort of defines this tensor. But you can see that we can efficiently retrieve that element by multiplying these matrices. And that's an efficient thing to do. If we had to save all the possible elements, that would be an exponential amount of things we'd have to save in the computer. I'll make that point a few different times, I guess. So the key adjustable parameter of a matrix product state is called the bond dimension, and then in math is called the tensor train rank. And the idea is if we have a tensor where all the visible or external indices, physical indices, have a size little d, that would have d to the n numbers inside it in general. We'd have to store that many numbers. That's why exact diagonalization can only handle small systems in physics. But if you use a matrix product state instead, I probably should have put an approximation sign here, but it just depends on how you think about it. There's this bond dimension, which you hope to not take to be exponentially large. You hope that you can take this to be 10 or 100 or maybe 1,000. And if you can hold it at about that value, you get a massive compression. If you just do some parameter counting over here, each of these tensors has chi by d elements, and there's n of them. So you have n times chi squared d numbers over here in general that you have to store. And that means this n comes down from the exponent and comes in front. So you have, at worst, a linear growth of parameters instead of an exponential growth of parameters. And you can do even better if you assume symmetries and things like that.
Question.
And then
question.
Yeah. Okay, what's the question?
Under what conditions does this compression work, and when does it not work?
That's a great question. So in a sense, I think that's actually a kind of a giant research topic, I would say, as you leave physics. As you go outside of physics, I think we don't know all the cases. I think basically we're just finding an increasingly long list of cases where this works. But physics, this is where physics has something to offer to the math field, is that we have a very systematic understanding so far of when these cases are. And the most prominent example, but I should say it's also growing in physics, I would say. The most prominent example, as many of you know, is low energy eigenstates of local Hamiltonians in one dimension. So the idea is that you have this notion of I can't go into all of it here, but you have this idea of the area law, or the boundary law. And we know that low energy states of local Hamiltonians obey that in pretty wide generality, and that's actually proved in 1D. And then in the 1D case, these matrix product states capture that. They reconstruct that case of the area law. But I should emphasize that that's not the only case. So we actually have now a lot of schemes even for representing finite temperature physics, where you can represent the states that you encounter with these as well. The trick there is just to not use eigenstates. You use other states, but you can actually capture physics across all energy scales as well with matrix product states. So it's a growing list.
Yeah, sure.
Yeah, sure.
Yeah.
Sorry, I had a follow-up question on this. So, so it means that then a modest bond dimension can capture systems with topological order in the ground state, right? Is that?
Yes. Yeah, that's right. So in fact, it's very, very easy for tensor networks to capture topological order. And this has been one of their great successes, I would say, of tensor networks, is they've been a really good tool for purely theoretical studies of topological order. So there's a really elegant papers like by people like Michael Levin, for example, constructing these string net states as tensor networks. I think Brian Swingle was involved in that work a lot, where you can actually write down a gigantic number of different classes of topologically ordered states precisely as tensor networks. And that was used again recently in a paper on isometric PEPs by Paulman and Zaletel, for example. Yeah. So one term that's, I think, slightly misleading there is you'll hear the term long-range entanglement talked about, and that makes it sound like there's a lot of entanglement. I would say that's not really the right idea. It's not that there's a lot of entanglement, it's just that it's kind of global or it's important, but it's actually not that much.
Thank you.
Mm-hmm. Okay, great, thanks for those questions. But one thing I should say is when I was talking to some people early on about using these in machine learning, one comment I got a lot was they said, well, why would machine learning obey the area law? And I didn't know, but I don't think anybody knew. So I had a bit of just a bold kind of engineer's attitude of let's try it and see. And it's sort of interesting. I mean, we don't have a reason why it obeys the area law still. It doesn't, there's not like a local Hamiltonian involved, but they do work. So I think it's a bit of a mystery still. So we can get back into that in the question time. One other thing about tensor networks, or a few other things, is that they have kind of very powerful algorithms that they enable. So you can't even really store a large tensor, much less compute with it without exponential cost. But with an MPS, you can actually sum to MPS in a controlled manner and get the result as an MPS and recompress it controllably. You can multiply MPS by other tensor networks and controllably produce the result with bounds on the error. It's very elegant. You can actually, if an MPS represents a probability distribution, as it often does in physics, you can do perfect sampling of it, meaning generate samples that are like true draws of the distribution every time without autocorrelation effects leading, related to the previous samples. So they have all these really nice properties. And as I mentioned briefly, in physics, we have a very rich idea, or kind of a really well-developed idea of when a particular kind of tensor network is suited for different kinds of data. And I put that in quotes here. Here, data in this context is like typical samples or measurements of a quantum wave function. So we know that, say, for gapped 1D systems, I should have said gapped earlier, by the way, when I mentioned the area law. When you have a local Hamiltonian with a gap in 1D, then we know it's been proved that matrix product states can do the job. But when you have a critical system, you actually need this extension called a mirror in order to really reproduce the right properties to all length scales and to all distances. And then in 2D, there's this idea of a PEPs tensor network, which is like a 2D extension of a matrix product state to follow the connectivity of a 2D lattice that can reproduce the area law in 2D. So we have this kind of really systematic understanding of which tensor network you should be working with for different situations. And just they practically work very well. So they can pull off very impressive and very powerful calculations. Like, for example, you can get extremely precise wave functions of thousands of three-dimensional atoms. That's something I was involved in doing. You can also do infinite systems in 2D of correlated electron models and get state-of-the-art results for things like high-temperature superconductivity, properties with stripes and all kinds of details, and sort of tying state-of-the-art results from other methods. So they're very, very powerful. So this, it just makes one think like, if you can do all these things, then how could they sort of not be useful in other areas? Is this the only possible use of them? Is it just for these problems? Why not try them on other things? And so indeed, since the late 2000s, the math community has been getting wise to this. And there's actually, we're totally parallel developments in the math community disconnected from physics, where people like Hackbush proposed the idea of it's called hierarchical Tucker, but it's equivalent to a tree tensor network. And I think that was 2006 or so. In 2011, Oscillates proposed the tensor train, which is equivalent to a matrix product state. And then those over the last decade have kind of gradually taken off and gained popularity, and people are finding more and more uses of them. You can see studies of discrete wavelet transforms, doing principal component analysis, which is like a kind of large SVD, and using them on data and all kinds of uses. And now there's conferences where people talk about tensor trains, and there's a lot of different people exploring it. So I would say that really the right way to think about tensor networks is they're a very general tool for doing linear algebra in exponentially high dimensional spaces. And so that they just kind of happen to have this physics pedigree, but that's just because, you know, physicists are sort of into crafting tools to solve their problems, but really these could have been discovered elsewhere. And I would say that notions that we think of as being very peculiar to physics, like entanglement entropy, really can be thought of as just notions like multilinear tensor rank. So rank is the idea that you do an SVD and you sort of just say how many non-zero singular values are there. But if instead of just saying how many zero versus non-zero ones are there, if instead you did kind of a weighted version of that, where you said, well, I'm going to count the larger ones more and the smaller ones less, you might do that through an entropy, and then they would have an idea of this entropy, maybe not entanglement. That's definitely more of a physics concept, but I think all these ideas can be sort of mapped over. And as I mentioned, these are already being explored in machine learning. We'll come back to some examples. I'll just put that up there more for those of you who want some references. So kind of to, let me go a little more quickly. To motivate this set of models I'll talk about, my motivation partly is to see how people were using them inside of neural nets, but to say, why can't we just have the whole model be a tensor network? So instead of just putting them into a neural network, why don't we let them breathe, so to speak, and the whole model be a tensor network? And you know, again, the motivation is, can natural images really be more complex than quantum wave functions? Totally. Also, if this works, we could import a lot of techniques from physics, and we could also re-import ideas from machine learning back into physics and improve tensor network methods. So let me tell you one way of doing this. It's pretty general. So we need these elements. We need data, which we can think of as input vectors X, and labels, because I'm thinking of supervised learning. And then we need a cost function to optimize. There's different ones. So here's a very common one, which is just this squared distance, L2 distance between our objective function, between the function we're training and then the objective function. And we need a class of model functions. So that's the main place where we're going to put a tensor network. So how can we cook up a class of functions where on purpose a giant tensor appears? And if we can do that, then we can replace that giant tensor with a tensor network and see how it goes. That's basically as simple as it is. So really, anytime you can whip up a function where a giant tensor with lots of indices appears, you could always, in principle, try replacing that tensor with a tensor network, and then see what kind of mileage you can get. So the simplest way you can think about doing this is a paper that came out the same week as the one that I published on this, but I liked their way better, actually. It's even simpler. It's to say, let's have the tensor indices label powers of a polynomial. So the input of our function would be these input vector components x1 through xn, which could be pixels of an image, and say these are grayscale pixels. So maybe each of these numbers x goes over 0 to 1. So then as we take higher and higher powers of those numbers, we're weighting them kind of less and less, but we're also making the model more nonlinear and more powerful because their numbers less than 1, right? So the higher power we take, we can sort of, there'd sort of be a controlled limit there. And then if we write a giant polynomial where these x's can appear various numbers of times and make all these different terms over different products of these x's to different powers, then naturally we can label the coefficients this way as w, n1 through nn. And then that just is a big tensor with n indices, where n is the number of pixels. And then these indices run over the different powers that we were willing to take of these pixel values. Okay. So if we kind of write that out, for example, we would have a constant term, then we'd have a bunch of linear terms where each of the pixels appears in its own term. Those of you who know about the idea of a linear classifier in machine learning, that's already included for free in this model. That's the first row. But then you have these higher order terms too. You have what people in machine learning confusingly, I think, called interactions, where you have like 2 of these x's appearing and you can have more. You can even have all of them appearing. Say if you have 5 pixels in this case, you'd have all of them in some last term in this polynomial. In a more general case, you could use really any basis of functions you want. They don't have to be powers of the x's. It could just be arbitrary functions that are labeled by these n's, right? So these phi's could be any function you want. And the ends just label which function you pick to plug the x into. So if you pick 1 and x, then you'll get these polynomials again up to a maximum power of 1 of each of the variables, but it'd still be a nonlinear model because you'll have things like x1 times x2, x1 times x2 times x3. Or you could pick phi to be cosine of x, sine of x, and then you might be able to bake in symmetries that you know. Like, for example, you might want the symmetry of x goes to 1 minus x of your model. Or you might just have reasons to think this is a nicer model to optimize over because the phi remains normalized no matter what x you plug into it. And that's the one that I picked in this paper that we used to try this idea out. And then the main idea, as I mentioned, is to say the coefficients, all the adjustable coefficients fit into a big tensor. And so why not just try making this into a tensor network or approximating it by a tensor network? And here I'm showing in matrix product state, but it could be any tensor network in principle. It could be a PEPS, it could be a Mira. And basically those choices would give you different amounts of power of the model, and they would make it harder or easier to figure out how to optimize the model. So PEPs are rather challenging to efficiently optimize. Matrix product states, you have lots of ways of doing it. And then that's the model. So basically you now have a matrix product state of coefficients times this basis of functions. All your adjustable parameters live in these tensors. And then what we want to do is simply minimize over these adjustable parameters, minimize the cost function. So we want to just say, let's compute this cost function, compute a gradient of it, use the gradient to update these parameters, and keep doing that over and over again until we're satisfied, and then apply the model. But you don't have to use a gradient. That's one very interesting thing about tensor networks, is that they actually afford all these different ways of optimizing. I'm not going to list them all, but we can talk about them maybe later. And what do you get as a payoff? So one immediate payoff you get, this is just to show the kind of different benefits you could get from this idea. You get adaptive weights, which is something not often seen in machine learning models. And the way in that paper in 2016 that I showed you can get adaptive weights in this case is you can do something that's built off DMRG, which is the idea of two-side updates. So you just merge two of these tensors together. You say, I'm going to temporarily sum over this index, and it's gone. And now what's left over is a tensor with 4 indices here in the middle. I'm going to freeze these other tensors at this gradient step. This is a choice I have. I'm just not going to update them. I'm only going to update this one. I'm going to update it a few times, just keep doing gradient optimization on it until it's better, meaning the cost function has gone down. Then after that step, I'm going to do a controlled singular value decomposition with truncation of this tensor, cutting it here, sort of treating these two indices as row indices and these two as column indices and doing an SVD. And when I do, it'll break it back apart. I can just push the singular values over into one of these tensors, and I get 2 tensors afterward. And then I can actually look at the spectrum of the singular value decomposition, and based on that spectrum, I can grow the index or shrink it adaptively to keep the solution of my problem at the same level of quality. So the problem may be asking for more parameters, or it may be actually saying, no, I don't need more parameters. Actually, I'm fine with less parameters. And that's what I saw. I actually could see that, like, out at the edges, where there was less information in the data, the bonds would actually shrink to 1. There was no learning to be done over there, for example. But in the middle, it would grow. So that's just a very, very kind of quick and dirty explanation of how this idea works, without going way into the technicalities. So let me now turn to talking about some, how well did this idea work? But this would be a good time to ask some questions if you're not too familiar with how you do some of these steps, like how do you minimize over these parameters? Okay. So
Ashar has a question.
Sure.
Sorry, I have a question about this last issue that you observed that there is more bonding in the middle of the chain rather than. Can it be an artifact of the way you define the cost function?
That's a good question.
You need to weight a little bit more the middle one rather than the edges.
I think not. Well, okay, sort of, yes. I mean, everything depends on the cost function a little bit. So, but in the end, let's say the best time to think about it would be when you get toward the end of the optimization. So let's say you really settle down into very close to the sort of the global minimum, let's say. Then it's sort of really a property of the, well, no, I guess it has to be the cost function, because it's sort of trying to leave the manifold of the matrix product state bond dimension you're currently at. So it's like the cost function is saying that there's a better solution to be had for an MPS of larger bond dimension somewhere, So yes, it is, but in a sense, no, too, because the cost function is probably, that would probably be true of any reasonable cost function you would write, because you can sort of always fit the data more and more closely. For any sensible cost function, we'll try to do this if you don't regularize it very heavily. So it's a good question, but it's a little complicated. So I'd say basically it is, but it would be true of almost any reasonable cost function, yeah. Thanks.
There's also a question from Joseph, I believe.
Okay. Sure.
Hi, yeah. My question is kind of, it's probably simplistic, but it's my understanding of what each individual node represents. So I think you labeled it a PEP, so the two-dimensional case, you know, where you add a 2D grid or and lines of nodes at the bottom. So I'm kind of visualizing this to try and basically adapt this image to a large matrix, you know, of the size. Are each nodes of these, are they like smaller matrices and the size depends on how far interactions go? So for instance, if it had nearest neighbor interactions, would it only be a 4x4 matrix, and then you can somehow write a whole Hamiltonian as some link between loads of 4x4 matrices? Is that correct in the way I'm thinking, or not?
I think you're in the right track. So they are like matrices. So they are basically in the computer, you know, there's different ways of storing them. They're also kind of like functions. So you might store them other ways, but a common way to store them is to store them as a list of numbers. You know, if you think of a matrix as a tensor as just a high dimensional array, which is true if you're thinking of a specific basis. So then that's how we store them. You know, we store them as a high dimensional array. So they're just a collection of numbers. Now, a good question you asked is like, is the amount of numbers or the complexity of these things to do with the Hamiltonian? So yes and no. More no, but sort of yes. First of all, here there's no Hamiltonian, so so they can't have to do with the Hamiltonian here because there isn't one. Even in a case where there is one, and these are ground states, then indeed, yeah, they kind of, the amount of numbers you need to do a good job often is related to how complicated the Hamiltonian is. But the complicatedness is not really to do with how many terms are in the Hamiltonian. It's more to do with, it's more of an emergent thing about, say, whether that Hamiltonian is tuned near like a phase transition or not, or something more like that. So as you could see in famous examples like the Ising model, it's deceptively simple, or even like the Hubbard model is maybe even a better example, where you just have nearest neighbor hopping or nearest neighbor spin interactions, and maybe on one other thing like on-site field or on-site interactions in the Hubbard model. And yet you can have this incredible, you know, amount of complexity of the ground states and the excited states. And that's really what determines how complicated these need to be, is that emergent property of the ground states or the excited states themselves, rather than the Hamiltonian, how it looks or what structure it has on the surface. Did that help you?
Okay,
Yeah, thank you.
Question from Jay Chat.
Hello. So I wanted to ask about the hidden features, which hidden layers in a conventional neural network, and how in general the wisdom is that increasing the number of layers somehow increases your efficiency of the neural network. And how does that compare to this formulation of the problem? So how would you, so to speak, increase the complexity or improve your tensor network?
Yeah, that's a great question. I think, so one thing about, I may not be able to really answer your question, but I think my answer is that I'm not really convinced anyone really has answered that question. I think it's a great question that people have identified and talked about a lot, but I think it really, here I might be being a bit, you know, pejorative or something to neural networks, I don't know, but I think actually a lot of people I know would agree with this, that there's a lot of really good questions we have about neural networks, but we have a lot more questions than answers, or hypotheses than sort of definite answers coming out of that field. So one of the hypotheses that people have observed or remarked on is that maybe having more layers of a neural network makes it, you know, train better, work better, generalize better, all kinds of things could be better. But we don't have one kind of really dominant convincing theory of why that is. And there's even, you know, counterexamples where sometimes it's not true and so on. But you're right, it is a thing that people have discussed very, very seriously. So one thing more generally in neural networks that's lacking is just sort of a very clear way to do theory. in a sense of really posing questions and then sort of definitively taking steps and answering them in a way that everybody can agree on. So I think that's one of the more compelling things about tensor networks, replacing neural networks. So if you do it as I showed here, where they kind of go inside a neural network, it's very, very powerful if you want to work with neural networks. But if you actually use the tensor network as the entire model, then we can actually think about questions like, does the data have an area law, so to speak, in a quite literal sense? Like, is the data captured by a low rank model, meaning like a tensor network of small bond dimension? And that's the kind of question you can ask, and you can really answer that question definitively. And in the talk next week, I'll show you can really construct a theory of learning of one of these particular algorithms. So I'm kind of skirting around your question, but I think basically I don't know if anyone knows the answer to that question, and I don't either. But I think that tensor networks could give us a way to ask questions we have a better hope of answering, like that.
Okay, I see.
Hope that,
you have to think of it
like
parallelly along with the
sort of
existing,
parallel, yeah.
Yeah. Thank you.
Mm-hmm. Thanks. That's a good question. Yeah.
No more questions for now, I think.
Great.
There's about 2 minutes left.
Okay, great. I'm almost done. Let me just say, I left it very sketchy how you do the optimization. And part of me is wishing I'd maybe put a little more details here, but on the other hand, it's okay because we can talk about this more. But part of it is the point that there's really a lot of different ways of doing it. But in general, what you can think about, how do you actually optimize these different tensors? Just kind of the simplest way, think of it as A/B testing. You come up with a proposal for a better tensor, you put it in, and you see if it helps. That's really all gradient descent is. And then you just have different formulas for how to propose a better tensor try to put here to see if it helped. But then there's really more sophisticated ones. As I'll talk about next week, I'll show a very different algorithm from that. That's more of a direct learning algorithm, meaning that you just basically compute the tensors one by one from the data. You basically do a double loop over the data. And when you're done, you get a small matrix, you diagonalize it, and it just gives you the first tensor. Then you do that again, and it just gives you the second tensor. And it's just like boom, 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 boom. And you're done at the end. And you don't even, that's it. So there's actually all these different ways of optimizing these with tensor networks that you can't even really imagine doing for some of the other kinds of models. So that's why I find this kind of fascinating. So in my last little bit of negative remaining time, let me just kind of, definitely don't want to skip over this part, is how well does this actually work? Again, I think the most interesting thing about these is not to try to use them because they're going to or do work better than everything else in every case, which isn't the case. But it's more because of those other reasons I said about exploring different training algorithms and theory and all these things. And yet they do work really well in lots of cases. So let me just tell you. One of them is this MNIST handwriting task, which is it's not the hardest task in machine learning, but it's sort of an important one to make sure you can do. And you can very routinely get 99% accuracy on training and tests. So we did it in 2016, and then very recently I was pleased to see this team at Google was easily able to reproduce that result as well. So that was great. Also, there's this much more challenging one called fashion MNIST. It's a drop-in replacement for MNIST in terms of image sizes. It's much more challenging because you have this very diverse set of clothing images. And you can also routinely get 89% test accuracy, which is very, very good. It's very similar to what you would get if you just kind of got an off-the-shelf neural network and trained it yourself. There are better results, but most are about 89%, in fact. That's for supervised learning, meaning just figuring out how to label these properly. Generative modeling is when you're trying to just take data and then see if you can generate new examples. That's also been done with matrix product states. So that's been done for MNIST, and these two different papers are good examples. So you can see as they use bigger and bigger and bigger bond dimension of the MPS, they get crisper and crisper images. And then there's this nice paper too by James Stokes and John Turilla, where they do generative modeling of a very challenging synthetic data set called the parity data set. It's kind of like a GHZ state. And what they do is they show there's like a geometrical optimal learning algorithm, like optimal local step you can do rather than using gradient descent. So it's a very nice bit of work. There's also these extended results where you kind of string together different MPS and make what's called a string bond state. And then you can actually get really state-of-the-art results in fashion MNIST. You have to do some additional tricks, like pre-process through one neural network layer and some things, but you can actually get state-of-the-art. I'm going to skip these slides for the sake of time. Well, one of them I want to briefly touch on, which we can come back to, is to say that you can run these algorithms on a quantum computer in principle. And by doing so, you get really interesting benefits. Basically, you can train models where you can use a finite number of qubits to train a much larger model. Or this is actually a physics paper, but it kind of ties in. You can actually train an infinitely long MPS on a quantum computer with a finite number of physical qubits. This is some recent work by Andrew Green and Frank Paulman and others. They might even talk on later in this conference, but this could be used for machine learning too. And I want to just skip ahead. I already kind of talked about a few of these just to say there's been a few really recent papers I want to highlight that I'm quite excited about. So one I won't touch on too much, but it's using these tensor network machine learning approaches here at Tree Tensor Network to learn physics data, which is, these are events in a high energy physics collider experiment to try to determine the charge of a certain quark based on these events. And both a neural network and a tensor network were used side by side to just try two different ways. And they both gave excellent results. The tensor network worked really well. And then the paper does a nice job of kind of highlighting some of the benefits of the tensor network and showing some of its different characteristics as a learning tool. One that I'm very excited about just came out just really a week or two ago by this team at Google X, including Geoffrey Vidal and Stefan Leichenauer and some of the people involved there. And they use this new architecture, new for machine learning, called a locally purified state. It's kind of like a square of two MPO tensor networks to do anomaly detection. That's where you basically look at things like images or data, other data, and you say, all of it is on a sphere by construction when we train, but then when we test, some of it falls inside the sphere, and we call those anomalies. So those might be images that are different from the ones you train on. And they actually found that it's state of the art on tabular data. So tabular data is kind of like irregular data, like medical data or like data about different forests at different altitudes and whether they have certain, seasonal characteristics and so on. So it's this very kind of heterogeneous data sets. They compared to a few different state-of-the-art methods, including support vector machines, and this one, which is a neural network, deep neural network approach. And the tensor network was the best in all the cases. So I was very excited to see that. Last example is you can do quantum process tomography. This also came out a couple weeks ago. And this is the first scalable approach to quantum process tomography as far as I know. And it's using a tensor network as well and getting really great results. Okay, so that's all. Just wanted to leave this up, and thank you.
Okay, thank you. Let's all thank Miles for a great talk. Under difficult conditions too. So now we've got 15 minutes of questions. Raise your hand if you'd like to ask a question. Jorge.
Yeah, I have a question. You very clearly highlighted that these diagrams are very, very important to enable us to think in this way. Do they have a name? Like Feynman diagrams are named after Feynman. Who started drawing these diagrams?
Penrose is usually attributed these.
Thank you.
So often they're called Penrose diagrams. But there's actually been a number of other people who've discovered and rediscovered them in the math community too. Thanks. But they've also been called string diagrams and other things too. Yeah.
Sam, you have a question.
Yes, so in all of these examples you gave, somebody has a problem and then they draw a network of some geometry and they use it. And what's the process that goes through their mind of trying to decide what geometry to use for a particular problem?
I like this question. So in neural networks, I'm not an expert there, but there's sort of a process of kind of sort of like, people will just try different, there's sort of different prevailing beliefs about how, that more layers is going to be better for a certain kind of thing, or a certain kind of initial layers, convolutional layers, will be better for images. And basically there's just sort of, it's kind of like density functionals in physics. You just have these different ones that you can't prove are better, but they kind of do these broad studies. And then over these broad studies, a sort of community wisdom will arise that these are starting to work well on all these kinds of, someone has their microphone unmuted, by the way. We'll do these broad studies and kind of develop a collective wisdom. So what I'm hoping will happen is that if we have other approaches in the future, maybe tensor networks, but maybe it won't be, maybe it'll be something else. We can do a rather different thing in the future, I hope, which is like to take the data, do some kind of summary study of the data itself, and then compute things like entanglement, so to speak, or like more like in math, it would actually be the idea of a kind of a rank, like estimate a rank of a matrix of breaking the data into two pieces. And then from doing a kind of quick and dirty study of these kind of bipartition ranks of the data, actually say, okay, a matrix product state would fit this data, or no, you need a tree network instead because of the growing rank in the middle or something like that.
Okay, Joseph.
Mm-hmm.
Joseph, you have your hand up.
Yeah. So my question is more about the sample data. So my limited knowledge of neural networks is basically that, well, I have no knowledge of them, but I always think of them as like, I hear them described as a black box. So for instance, you give them a sample set, you train it on a sample set, and then you kind of let it go. And you know, and then you see how good it is, and then everyone goes, oh yeah, this is great. And then they find out like it's been trained on a sample set that gives biases, but because it's a neural network, it's very hard to find those biases, because ultimately it's hard to probe down in them. So with these tensor networks, is it easier once these biases are kind of detected to kind of correct them and identify where they are because you can analyze individual bits?
I like this question. So I would want to be cautious, and I can't claim it's easier, but I do believe it could be, and I have sort of lots of reasons why I might think that. So that's sort of under this heading here of much work to be done. So we would need to really show that, and of course, some of this gets into topics that are hard to define. You know, how do we really define the bias and so on? And it might be in the data itself, so we'd have to be careful there. But already there's some promise. So this paper, this very recent paper, is kind of showing a little bit of how to begin doing some of this. And one of the things that they do is they have this very nice geometric picture of what's going on. Now, I mean, you might also be able to have some of this geometric picture with a neural network. Don't get me wrong there totally, but with a tensor network, you actually do have this nice ability to kind of think globally about what the thing is. You can say the weights are kind of one gigantic tensor, as well as being made of all these smaller pieces that make the method efficient, and you know, we can do local optimizations. But once we've done that, we can also step back and think about all the weights as one big tensor. And what I didn't show on this slide is that they regularize it by tracing over all these black lines, which are these external indices. And that's a very important part of their anomaly detection setup. And that lets them to say that the weights like kind of define the sphere, and then anything that falls too far away from the surface of the sphere, that's an outlier, you know? And so one could even do this just on data as a preliminary study to say, this data is biased because supposedly we have these two different classes, but actually one of them is much more anomalous than the other, and they're not really well distributed over their example, something like that. So because we have these geometric interpretations, I think, and other reasons as well, I think there is a good amount of hope of what you're asking to happen.
Okay, how about let's one from Timotheus Tula would like to ask a question.
Right. Hi. I wanted to ask you a question about the method that you mentioned of extracting the missing data from the learning sets using the tensor network. Could you expand on that, or maybe give a reference?
Sure. I don't have a reference right away, but I can just tell you, and we could, if you want to email me, we can talk about that, and I can try to put some in the next talk. So basically, this is a building on a very old idea in machine learning that's often under the title of recommender systems. And there, what you would do, the key example would be like Netflix. So you would have a matrix, and the matrix is just like an Excel spreadsheet. It's like the rows are just say people, and it's just different Netflix viewers, like ID'd by their ID number or something, or account number. And that would think of that as being very, very, very long, like millions of examples. Then think of the other way, the column, as being movies. And that might be kind of large, but not super large. It might be 100 different movies. Then everybody puts stars for which movies they watched. So they might put a number that's between, say, 1 and 5 in places where they watched a movie. But as you can imagine, a lot of the entries are missing because, you know, most people haven't watched all the movies, right? Now what you can do is you can take that matrix, that like Excel spreadsheet, and you can just put it into like an SVD package. You can just do a singular value decomposition of it. Then what happens is that basically all the kind of small singular values are having to do with keeping those 0 entries to be 0. That's kind of what they do. They kind of enforce this irregularity and these kind of noisy, these like very fine details of the structure, which is that all these very, very specific entries are 0. So when you remove the small singular values, all that's left is kind of the trends. So when you remove the small singular values and then put it all back together, those missing entries appear. They become non-zero. And in fact, they often happen to have very reasonable values. So they tend to put weights in the movies that you would like to watch based on the other ones you watched. And the way to understand that is that the singular vectors are like explaining latent, they're like latent explanations for why the people rated the movies they rated. So they might have to do with genres or tastes and things like that. So then all a matrix product state is, at the end of the day, is just a multi-SVD. That's really all it is. It's just taking a multi-way matrix, if you want, with rows, columns, and so on and so on, and some multi-columns, you know, and just SVDing it among all the bipartitions. So then, just as that happens in the matrix SVD, it would also happen in the MPS. And so that's being explored quite a bit in the TensorTrain community, and it's something I think is a bit alien to physicists, because we think of those truncations as being error, but they're actually restorative when you have you don't have all the data. So I think that's something we should explore more with tensor networks, and it's not been fully explored.
Okay, Jan von Delft.
Yeah, nice talk, Miles. I was wondering whether in your study of the neural network literature you've encountered methods that you would say that's exactly what we need when studying quantum systems with tensor networks.
Let's see. So, you know, when studying neural networks, let me see. I'm not, you know, I don't know if I have so many examples springing to mind right away. You know, I guess one of my favorite neural network studies, though, that ties into physics is these recent studies, one by a team in Google DeepMind in London. I think the first author is Fao, and like PFAEU. There was another very similar work at the same time by Giuseppe Corleo and collaborators on how to create fermionic tensor networks, or sorry, neural networks. So how to make a neural network that has, that always makes an anti-symmetric function, so that when you can optimize over it. I think that's, you know, some really nice work, and they were getting state-of-the-art results in quantum chemistry. Now, there already are ways to do that with tensor networks, as you well know, and as many people know. But that's an example where some of those creative approaches could probably be, you know, looked at again, as maybe we have other ways of doing that. And you know, another one might be some of the okay, this is definitely a big one, is optimization techniques. So this was already done, as you may know, that there was a really brilliant piece of work by Lei Wang and collaborators, where they said, why don't we use automatic differentiation frameworks and packages and software to do infinite PEPs? And when you do, it has all these benefits, and you get really state-of-the-art results for IPEPs using these kind of pre-existing packages, including, but not limited to, you know, GPU acceleration, but also very, very smooth optimization with very, very smooth and kind of systematic convergence.
There's a question here from the text, the chat, from Philip Sushlands. He says, thank you for your talk. I have a question. You talked earlier about the interpretability. I would be glad to hear more about the possibilities of interpreting the results of tensor networks in the realm of machine learning.
Great. Yes, so this is another one, kind of like the question about having many layers and so on, which is a great question. But I think it's almost one of these questions that's so big that that what we need is really better questions and better frameworks to really crack into it. So what I kind of mean by that is that I think that rather than thinking of interpretability as a thing that we know what it is, and then will tensor networks help with it, I think tensor networks will actually help us to even figure out what we should even be thinking of as interpretability. Like I know that sounds grand, but I mean, I just mean that just like with wave functions, where we didn't really think about as entanglement as much as a useful thing until we had DMRG to think about it through, you know, that it helped us to, there were other reasons to think about entanglement, but the DMRG was a big motivation to look into it more. Similarly, I think by bringing tensor networks into machine learning, we'll have really good questions about interpretability to ask. So one of those would be, which tensor network is the best one to use for a given data? I think that is a kind of interpretability. And I know that sounds like a very tensor network centric answer, but I think really that's just saying like, how low rank is the data? You know, is the data high dimensional or low dimensional? Does it live on a simple manifold or a very high dimensional manifold? Things like that. And I think we could pose nice studies, which I've already begun doing a little bit, and other people have done, of course, too, where we actually study systematic classes of synthetic data, like little bit string data sets of even and odd bit strings, or bit strings with little clumps of ones clumped together with different power law or exponential correlation functions. A lot of these we've essentially already studied in physics under the guise of spin models, but we could kind of put them through the pipeline of machine learning too, and start to have classifications of data and say, this is data that's hard to learn in a fundamental sense, or this is data that's easily learnable by an MPS. And then if it's not working, we know it's the training algorithm, it's not the model, and so on. So that's some examples of interpretability that I would envision people doing.
Okay, that's great. Kazuaki Taka-san.
Hi, can you hear me?
Mm-hmm.
A little bit similar question of the as previous question, but I want to know the applicability of the MPS representation for general dataset. And so, yeah, as you show, the MNIST dataset can be learned using MPS representation, and as you know, as you said, MPS can be applied to the one-dimensional local quantum system with area law. So, does it imply some MNIST dataset has some property like area law, or such kind of some good property about entanglement or something like that?
So that's a great set of questions. I would say, first of all, I would be a little careful to use the word entanglement in these settings, because personally I would use that to mean like you have a probability distribution where you square the parameters to get the probability, and then you have density matrices. But definitely I think we can talk about the kind of the rank and the entropy of bipartition of the distribution that the MPS is modeling, or the function. It doesn't even have to be probabilistic. So we could talk about splitting the function and looking at the rank of it, and then saying what's the kind of the entropy of that. So, but actually in the case of MNIST, I think it's a bit like how we use DMRG for 2D systems, where we kind of force it. I think we're just trading on the idea that MPS can actually, they have a lot of raw power. They can brute force very complicated functions over a short distance. So you can basically, even though they have to decay exponentially at longer distances in terms of the correlations that they can produce, over short distances, like order of 10, 20, they can fit very complicated functions. So I think to some extent, it's just a bit of a brute force case. That's just an opinion. I mean, I think more study would have to be done. So I think really where MPS could shine, and it needs to be done a lot more, I think, is to, and actually I glossed over a slide where it has been done a little bit, is to do things like one-dimensional data, like time series. So it could be like audio, text, speech, you know, time trends, temperature data. You know, I think there's a lot more there. And I think there could be beautiful interpretations that could be done there, where the bond dimension could be sort of different kind of latent information explaining why what happened before connects to what happens after, and so on. I think there's probably a lot to be done.
I see. Thank you so much.
Yeah, thank you.
Yasha Komajani.
Sorry, I have two questions. One is that it's about the tensor product states, or metric product states in general. Is it possible to search for nearly integrable models? For example, for example, in the Heisenberg model, I know that in spin 1, if I add a term with a biquadratic term, I can make it integrable. Do you know of any work that I could feed in some generic Hamiltonian and try to search for some integrable points in this, like the multidimensional?
That's a great idea. I would say yes. I think that could be a very well posed question. I think like the way I would envision it would be, I mean, because you know, I'm seeing people do things that seem just as hard to me. So this paper, they're literally working out a CPTP map, like a map that's like similar to a noisy circuit applied to a density matrix. And they write it here in this thing called a Choi matrix. It's just sort of this tensor network, and as far as I see it. And it's basically something that just eats pure states or eats mixed states and spits out other mixed states. And they were able to sort of reverse engineer that map for different noisy quantum circuits and other random quantum circuits and things. So you can see you can do some pretty difficult stuff with these. So I could envision a setting where you instead have this parameterizing a Hamiltonian, and you say, okay, we have a bunch of other operators that are represented as MPOs, and we want them to commute, you know, with this thing, and we want a lot of them. And then you basically penalize non-commuting of those, and you try to find the ones that commute or something. So I could imagine that. Yeah, that's a neat idea.
Maybe a different question. Can you elaborate a little bit? You said that you can use quantum computer to do machine learning. Can you elaborate a little bit more on this? How?
Yes. Yeah. So one thing there, I didn't leave enough time for that, but it's okay. Just more of an advertisement, I suppose. Is that you can one way to use tensor networks in machine learning is to have them represent probability distributions. So you just say that. Well, I had a slide way earlier, but I won't go back to it. But basically, where I have a matrix product state, let's say down here, and I sample from it just like it's a wave function. And then when I do, I treat the bits that come out, the zeros and ones, as like, say, black and white pixels, or they could be other information, anything you can encode into bits. And so then all I have to do, in a sense, is just figure out what numbers to put into the MPS, so that when I sample over it, I like the samples that I get, that they meet some criterion. And then it just turns out that, like, there's different ways of thinking of connecting this to a quantum computer. One way would be to say I train an MPS classically, meaning on a regular classical computer, like on a laptop, and I figure out a bunch of numbers that go into these different MPS tensors, like here, that generate samples that I'm happy with. Then there's always a way to read off this MPS as a quantum circuit. So skipping the stuff in between, I can sort of, there's a formula basically, or a prescription to sort of start here and just read off a circuit up here, where if I run this circuit without any errors, or with very low error, and then measure the qubits afterward, the distribution of these measurements will be the same as from this MPS. And that's another thing I like about tensor networks, is that, you know, there's just this kind of one-to-one mapping between circuits and tensor networks that other machine learning models don't really offer such a direct interpretation back and forth. So then one could ask, okay, is that all you can do? Or could you actually further say, once we did that, could you train the model more on the quantum computer? And indeed you can. So there's papers proposing various ways of doing this. If you parameterize the model in certain clever ways, you can actually flip the parameters of the model into special settings where the measurements actually compute the gradient rather than the output. That there's some works about that. Or you can just do kind of simple kind of gradient-free optimization methods, like kind of genetic learning algorithms, for example, to do that. And then finally, you can, by using tensor networks, you can devise these kind of interesting ideas like reusing and resetting qubits to actually, so here is showing we need, you know, what's this number? Maybe like 8 qubits to generate 8 outputs. But here is showing you can actually generate any number of outputs just using 4 qubits by just reusing them over and over and over. And kind of using some similar notions, you can do the whole DMRG algorithm on a finite number of qubits, but on an infinitely large wave function, like an infinitely long wave function. So I'm just sort of showing how that there's these kind of currency where you can sort of translate these ideas one to another between these different settings.
Great. Hector Leon, you had a question.
Yes. Hello, can you hear me?
Mm-hmm.
Hi. Yeah, so this is all completely new to me, but I thought I'd ask a question on when you went from a tensor to the tensor network and sort of what the price you have to pay for doing that is. So it seems to me that if you ask about the entry, you know, 1010 or something, and then you change the value of one of those tensors that goes into your tensor network, you're going to be changing the value of a bunch of other indices that also feature that one tensor, the one that you changed. So it seems that these things will be very much sort of interconnected when you try to optimize. I was wondering how you sort of work around that, or how that's taken into account in any sort of way.
Yeah, it's a good question. In the sense of like, yeah, like that's you know, that's even maybe kind of a question that gets even back to some of this interpretability question that was asked earlier, in terms of more of an engineer's question about interpretability of like, of saying, what will happen to my model if someone starts corrupting the data on one of the pixels, say, and feeding it in? Will the model just start to fail terribly, or would it survive that? But you're asking, I think, even more sort of math question about just what happens if I sort of start to heavily change one of these tensors. Is that the question?
Yeah, it's sort of
okay.
In order to kind of optimize one of the, maybe I misunderstood it, but like you ask for one entry, you decide to change the value of one of those, rank 3 tensors that you have in the product. And that necessarily changes the value of another entry if you ask for, the 0, 0, 1, 0 instead of the 1, 0, 1, 0. You're going to have changed that entry, I think. And so I'm just wondering whether you're kind of fighting yourself a little bit in some sense when you try to optimize.
It's a good question, but I think it's a little bit of a complicated one to ask and answer. Okay. But it's good. So I could just briefly tell you a few things I know. So one is that I believe, this is a bit of more of an intuitive belief, I'd have to sit down and think about it more, that still correlations amongst the tensor, and if you think of it as parameterizing a probability distribution, which it doesn't have to, but is often how it's used, then the correlations amongst indices, if you think of sampling back from it after corrupting or changing one of the tensors, would probably be rather intact, far away from wherever you corrupted that tensor, I think. So that's something that one would have to check. But probably like correlations across the corrupted tensor would be changed quite a lot, like sort of joint correlations across, probably. There's also an interesting work by Leon Valence where he actually looks at this in the context of physics a bit. He says, what if you have a tensor network that captures some kind of topologically ordered state? But then you just introduce kind of arbitrary perturbations to each of the tensors that are small. How robust is this description? Because he was interested, I think, in the question of people find these in DMRG calculations, and can they really be trusted if one sort of shook at the tensors a little bit? I think the answer was it depends, like unusual in physics, and there were sort of interesting cases he found about whether the perturbations respect symmetries and so on. So there's been some work on this, but basically, I'll kind of end by punting and saying I think it sort of needs more attention.
Okay. Well, thank you.
Okay, we're just gonna, since we're over and we're gonna start the student run session very soon, I'm just gonna allow one last question. Sure. He's had his hand up for a long time, that's Andrew Green.
Great, Andrew.
Oh, thanks very much. Thanks, Miles, for a great talk. So there's a Moore's law, I believe, for machine learning, and that's that the energy cost to train a neural network is doubling every 3 months. Do you think physics-inspired algorithms for training tensor networks can improve on
that? Great, I really like this question, because I'd have to say, of all the things about them that I am interested in, personally, I think at heart I'm kind of an engineer, so I really like algorithms, and so what I'm really trying for right now, but we'll see if it really happens, and it's already been done to an extent, but I want to try to make it better, is some kind of ideal of like a single shot sort of training algorithm for these, where you really run the algorithm one time over the tensors or over the data or something, and then when you're done, you just pretty much already have very acceptable results for the parameters. And there's a lot of things that make that kind of tough to really do, but I think it's not an unreasonable thing to hope for. And have it be linear scaling in everything, linear scaling in the number of inputs, linear scaling in the data set, and not just as an asymptotic property, but really straight away. So I think that has a hope of being very power efficient. Now, it depends on the details, how heavy are each of those intermediate steps, but I think it could be, and it could be heavily parallelizable. That's not a power efficiency gain, but at least a time efficiency gain. Trying to think if there's another answer to your question too. Maybe just also that if you have more like gradient methods. Oh, here's one other maybe what idea I've been wanting someone to do, or I'd like to do, is to think about carving off already done parts of the parameters as you go. So sort of like you train an MPS and you train it a while, then you say, I bet there's already a lot of frozen done kind of information here. Like maybe all the short distance correlators are great already, but the long distance ones are taking like a power law slow amount of time to converge. So what you might do is you might do a renormalization, a controlled renormalization of the model where you actually like peel off a mirror layer and you say, okay, I'm going to split this thing into an MPS